So in our first example over here, we have copper solid, which is copper metal, is placed into a nitric acid solution. Is the reaction spontaneous or non-spontaneous? So we're going to apply the 5-step method in order to do this. The first step is going to be to list all ions, which is basically anything that's involved in the reaction. In this case, it's copper solid. Now, nitric acid is a strong acid. And the rules that we had established previously were that if it's a strong acid or an ionic compound, you're going to split apart into ions. So HNO3, instead of writing that, we're going to write it as H plus and NO3 minus. So we're going to go H plus NO3 minus. Now, I'm going to do this part a different color. If it's a solution, we also always have what? A solution means that it is mixed in water. So we're going to put H2O always. And I want you to write this here. Underline this part and write always include in solutions. Or if it says that it's aqueous, which is a solution. So we got Cu solid, we got H plus, NO3 minus, and H2O. The next thing that we're going to do is we're going to label every single one of these as an OA, an RA, or both. Looking at our table, I'm going to start with copper solid. I see that I find copper 2 plus on this side, but that's not exactly the one that I'm looking for. I want copper solid exactly, and I see that it's on the right side, so that's going to be an RA. By the same token, we want to find water, and because it is one of the things listed, and we can see that it's also on the right side, so it's also going to be an RA. Now, we also want H plus with NO3 minus. We don't want them separately from the nitric acid. And when we look over here, we can see that there's an NO3 minus here and there's an H plus. Now I know there's coefficients, but the coefficients don't matter. So we're going to write coefficients don't matter for what we're trying to do. We just want them together and present. The coefficients are just balancing the reaction, which we're going to tend to anyway. So this over here, these two together are going to be an OA. So we got NO3 minus with H plus as an OA. We got H2O as an RA, Cu solid as an RA. And always check both sides. Just because it's on one side, it doesn't mean it's not going to be on the other side. We're going to check and see if any of them show up again. And when we do that, we actually see that water shows up on the oxidizing agent side as well. So it is also an OA. Once we have these labeled, we're going to go back and list them. So this was an RA together. This was an OA. This was an OA and an RA. And so that's step one. Step two says to pick the strongest. Actually, this is still step one. We're going to pick the strongest out of each. And when we do that, we see that your H plus and NO3 minus were in fact the closest to the top. So we'll put that as an SOA. And copper was closer to the bottom than water. So copper is going to be the SRA. And although we do have an extra OA and an extra RA in the water here, all we really care about is the SOA and the SRA. So now that we have the SOA and the SRA, we're going to write the half reactions for each for steps 2 and 3. So for the SOA, we go to the data booklet, and we see already the balanced reaction for NO3 minus at H plus. Well, we scroll up, it's right over here. So all we're going to do, remember, you're not rebalancing this reaction. we're just going to write that half reaction down there. And so there's our reaction for the oxidizing agent. Again, just copy from the data booklet. We're going to do the same for step 3, but it's going to be for the reducing agent instead. And the reducing agent is over here. So you saw it now. Remember, because it's a reducing agent, right, you read from right to left. So we're going to read it this way. That's because it gets oxidized, right? RAs get oxidized and they don't get reduced. So don't write the reduction reaction. I'm going to go Cu solid to Cu, whoops, let's just 2 plus, whoops. Okay, so Cu solid to Cu2 plus. And that's steps 2. Step 4 is going to be to combine these two, just like we would normally combine them when balancing half reactions. So we're going to find a common multiple if it's necessary. In this case, both of them are 2 electrons, so we don't have to multiply by any common multiples, and we'll just combine both half reactions and cross out any like terms. And so, of course, the like terms are going to be the electrons. Otherwise, everything else should stay. And so here is our final redox reaction. Now, the most important part is the SOA. So these two above the SRA, the copper solid. If it is, we'll have a spontaneous reaction. If it's not, we won't. Let's check our table and see. And so we're back to our table here. We look at the SOA as follows. We're going to find the SRA here. It's sorry, I did the whole thing, but what I actually should do is let's just do specifically the SOA part. So here it is. And then the SRA is over here. And yeah, I mean, we can see that the SOA is definitely above the SRA. And so that means that this reaction is spontaneous. And you would just write spontaneous in your work below. Okay, so we're going to commence again with just writing redox reactions and showing how they form. What I got here is a little chart that kind of serves as a good reminder for when we're writing these, and just, you know, kind of a revision of some of the rules that we were talking about before, which is remember that anytime you see aqueous solutions, you're going to include water molecules when you're listing all your ions. As well, when you have any acids, especially if they're strong acids, they're going to separate into H+. So like I had kind of mentioned before, if we had HNO3 and that is a strong acid, when we list these ions, they're going to be H+ and NO3-. As well, if it's a basic solutions like sodium hydroxide, for example, and this is pertaining to this rule over here, well, that splits up into Na plus and OH-, and we look at each one separately as an OA or as an RA. As well, what we saw is that in the data booklet, some oxidizing or reducing agents occur in combinations, which means that they require more than one thing. So if I look at the MnO4- in the data booklet, it actually requires H+ with it as well. So for example, when we look at the data booklet here, when we see MnO4-, so I'll highlight that one over here, we see that it needs 8H+ as well. And what that actually means is that MnO4- cannot act like an oxidizing agent by itself. And it's not the only one that has that as well. If you look at the perchlorate ions, they also need 8H+. If you look at dichromate ions, it also needs an H+ present. And if I look at, for example, I was mentioning nitric acid. Well, here it is, NO3- needs H+. So if H+ is not there, we actually can't use this as an oxidizing agent. And finally, some of these, like water, iron 2+, SN 2+, and chromium 2+, these can be both OAs and RAs. So make sure to always look on both sides of the table when we're deciding this. So let's take a look at a couple of textbook questions. Let's look at this one in particular. A lead strip is placed in a copper 2. So what this means is copper 2+, a copper 2 sulfate solution. When it says solution, remember that we're going to also include H2O as one of the entities. So let's figure out if this is going to be spontaneous or not spontaneous. And I want you to take a couple minutes and write this question down. Okay, so in this first step, we're going to list all the ions possible in the reaction, which gives us lead solid. So it said a lead strip, a solid strip, is placed into a copper sulfate solution. So because it said solution, we included water as one of the entities. And this would have been this compound, but since it's ionic, we split it into its ions. So hence we wrote it in its ion form right over here. Next thing that we're going to do is we're going to identify all the OAs and RAs, and we'll go back to the table for that. So when we look at the table, we see that lead is over here on the right side of the table. So PB solid is going to be in RA. So it's a reducing agent. When we look for water, we can see that water is on the left side, so that's an oxidizing agent. However, if we look on the other side, we could also find it by itself over here. And so it's also in RA. So water is an OA and an RA. Now, copper 2+, we can find it on the left side exclusively, so that's an OA. And then sulfate, SO4, 2-, could be in OA, depending on what else it's paired with. In this case, if it's paired with H+, then it's an OA. But in our situation, that's not the case. There is no acid present. There's water present. So SO4 with H2O together is an OA. And so we'll go back. Once we find them all on the table, we're going to go back and identify them right on our list. So here we've labeled all the RAs and OAs that we got from the chart. You see I put a little connector between the SO4 2- and the H2O to show that together they represent an OA. And of course, water by itself is both an OA and an RA. And all we're really interested in is the strongest of each. So when it comes to the RAs, we're going to pick between water and lead, we're going to pick the one that is closest to the bottom. And when we looked at our chart, that was the lead. So that's going to be the strongest RA. Now, when it comes to the strongest OA, we're going to pick the one that is closest to the top on the right side, on the left side, and that is copper 2+. So we have copper 2+ and lead as the strongest oxidizing agents and the strongest reducing agent. Now what we're going to do is we're going to write the half reactions that we got from the data booklet. So when you look in the data booklet, you're going to see the half reaction that's already balanced for you. Okay, the double arrow here for lead 2+. And then for, sorry, not lead 2+, but copper 2+. And then for lead solid, we're going to read it backwards, remember, because reducing agents get oxidized, so we're going to read the reaction in reverse. So it's going to be PB solid, which yields to PB2 plus 2E. Now, we're going to use the lowest common multiple to get rid of the electrons. So this is just like when we're combining our half reactions to make a full redox reaction. In this case, they're both 2 electrons, so we don't need to find the lowest common multiple, so they can automatically cancel. And we're just going to combine the two. So I'm going to write net redox reaction over here. And that'll be Cu2 plus lead solid. And that is going to give us Cu solid plus lead 2 plus. And remember, here is our SOA, and here is the SRA. And finally, to determine if it's spontaneous, we're going to see if the SOA is above the SRA. And if it is, then it is spontaneous. Okay, so when we go back to the chart here, we find copper 2 plus, which is the SOA, and the SRA from all the other ions listed is right down here. And we can see that the SOA is above the SRA. So this reaction is spontaneous, which means that it's going to work. You don't need to help it out with any extra energy. So it's spontaneous, the reaction works. All right, let's take a look at another one here. A last final one for the video. Let's look at C, because this one has a lot more going on. So it says potassium dichromate. So remember, and I'm going to change the color for this. Potassium dichromate is K2Cr. You know what? Maybe let's use a different color. Let's use red instead. So that's K2Cr2O7. Okay, and maybe I'll write it even up here. So that's Cr2O7. And it's being added to acidic, so we know that there's some H+. Iron 2, so that's Fe2 plus nitrate. NO3 solution, which means that there's going to be water in here. So we want to know if this is spontaneous or not. So I want you to pause this video and I want you to list all the ions that follow all the rules that we've done so far, and then unpause the video and see if you have what I have. So by now, hopefully you would have got something like this. So there's a whole lot of ions going on here. Now here comes even the trickier part. So one thing I do want to mention is that we split up the potassium and the dichromate. Dichromate is a polyatomic ion, so you don't split polyatomic ions, but we do split the potassium from the dichromate because it's an ionic compound. We also split the iron 2 plus from the nitrate because it is an ionic compound. We added H plus because it said acidic. Whenever it says acidic, always make sure to add H plus. And we added water because it did say solution. Now, I want you to pause the video and label all the OAs you possibly can get. And once you're done doing that, unpause the video and see if you got what I got. And don't forget to look for combinations and things that show up both as OAs and RAs. Okay, so hopefully you got something that looks like this. Now, what I will also add is that you can find H plus by itself as well as an OA. So here's a couple things. So K plus is an OA. It's on the left side, it's towards the bottom. Cr2O7 2 minus and H plus, although in your data booklet it's listed as 14H plus. Together they're an OA, so that's why I've put the purple connector between them. Fe2 plus was found on both the left side and the right side, so we called it an OA and an RA. NO3 minus, if you look at the data booklet, it requires 4H plus, so together, that's why I have the red connector here, together H plus and NO3 are an OA. And water is both the OA and the RA because it shows up on both sides. Now, what we're going to do for this part is, yes, there's several OAs and RAs. All we really care about is the strongest one of each. So remember that when you're comparing between RAs, the strongest RA is always going to be closest to the bottom of the data booklet. So right, closest to bottom. And the strongest OA is going to be closest to the top. So I want you to pause the video and I want you to locate between all of these, the SOA and the SRA. So by now, you should have seen that Cr2O7 2- and H+ are the highest on the left side, so they're the strongest oxidizing agents, and Fe2+ is the lowest on the right side as a reducing agent. So our SOA is dichromate that's been acidified, and our SRA is the Fe2+. Now we're going to write the half reactions that are shown in the data booklet. I want you to pause the video, go and find the half reactions, and write them as you see them. Remember, for the SRA, you write them backwards. So by now, you would have found these two half reactions. Now remember, if we're using Fe2+ as an SRA, then you have to look for Fe2+ on the right side. Don't use the one on the left side. A lot of people would get confused. If you use the one on the left side, you're using it as an oxidizing agent, not a reducing agent. So now what we're going to do is, like we've done in the past with our half reaction balancing, we're going to make sure that the electrons are equal before we combine them so that they cancel out. And to do that, we'll find a lowest common multiple. And between 1 and 6 is going to be 6. So I'm going to multiply this one by 6, which changes all the coefficients here. And then now we can combine them. I want you to pause the video, combine them, cross out like terms, and unpause the video to see if you got what I got. So after combining them, hopefully we got something like this. What we're going to do is cross out the like terms, which is the electrons. And then everything else stays pretty much the same. So whatever remains, this is going to be your final redox reaction. And the big question is it spontaneous? Is the SOA above the SRA? So is this here above this over here? Well, let's pause the video, look at our data booklets, and find out. So when I look at the data booklet and I find my Cr2O7 with the H+, and this is my SOA, and I find my iron 2+. Remember, I'm not going to look at iron on the other side. I'm going to look at it on the right side because I want the reducing agent iron. That'll be SRA, and we can see that it is clearly, the SOA is clearly above the SRA. So this reaction is definitely going to be spontaneous. Now I want you guys to, once you've taken all the notes down and you understand the contents of this video, I want you guys to go ahead and try this.